numerical model. So this work we have been developing with Elisa Popet and Gonzalo Ruiz. It's called two-level numerical model for the dynamic failure of fiber-reinforced concrete. So, well, I add some, I'm not sure if the mouse works. So I'm going to follow this index of the talk. And I'm going to start with the introduction, experimental observations, numerical simulation, and some conclusions. So because this is the second part of the talk, even though at the very beginning that Jaime Planas gave a very nice introduction on the cohesive models, but just for the Chinese students who are coming, I'll just give a brief introduction on the cohesive theory of fracture. So in comparison with the linear elastic fracture mechanics, the cohesive theory of fracture, what you can see is from the figure that, well, from this shaded area of the sigma versus opening curve, is that the fracture after started, it still has some resistance and it can transmit stresses between two crack lips. So on the right I showed is that we have basically the three, I would say, the main references. The first one, the 1962 by Barenblatt, and then the second one, which more attributed to the fracture in concrete by Hilbert. It's the model of fracture mechanics in 1978. And what you see is that on the right corner, which is the book of Bassam and Jaime Planas on fracture and side effect in concrete and other quasi-brittle materials. It's published in 1998. I would strongly recommend, if you have not done so, read this book. And I would just to emphasize two characters that comes with the cohesive fracture. One is called the characteristic length of Hilberger, which Hyman has mentioned before also. So it's just the combination of the material parameters, the elastic modulus, the fracture energy, and the tensile strength. And this one gives us an idea, especially if we do numerical modeling, and the mesh size should be like should be able to resolve this length. It's like normally we use like 1/10 or smaller mesh sizes. The second parameter is the intrinsic time scale. This is like brought out by Camacho and Ortiz in 1996. So again, it is just a parameter that is put together by material parameters. You can see the rho is the density, sin is c is the wave speed, longitudinal wave speed, and then it can be written as the characteristic length divided by the wave speed. So then I put the parameters for a typical microconcrete, in that its maximum aggregate size is like 5 millimeters. So I have the elastic modulus is 30 gigapascals, and Boson's ratio compressive strength at C, Ft, which is tensile strength, Gf is the specific fracture energy. You can say it is smaller than the normal concrete, and rho is the material density. So if we do the calculations, we have the wave speed, it's like 3,800 meters per second WC, which is if we have a linear decreasing cohesive law, and this is 2 times the GF divided by FT. So in this case, it will be 26 micrometers. And then the characteristic length is 104 millimeters, and TCH is 27 microseconds. So I wanted to put to this slide is just to show later on that why we can capture dynamic effects just using static cohesive law. So I think before, like Gonzalo has gone through like an overview of the experiment work we have done. So I should just like what we have used the cohesive fracture model. On the left, what you have the those two materials, they are concrete. So this is the dynamic cylindrical what is the indirect test, the dynamic one, and that down the left. On the right, it is a 3-point bending test, but with a notch on the left side of the middle section. So this our work published in AJAME 99 and 2002. The work was because the cohesive element model by Pandolfi and Ortiz. So this is the very early work that I had done many years ago. So what you see that this is the application to unidirectional fiber-reinforced composite plates. What you see here is that basically we are able to capture the shock wave structure at the interface. And there the cohesive model is like it is varying according to the angle with respect to the fiber direction. On the right, what you have is the simulation of advanced ceramics. So this is one of the figure that has shown that how we can capture the dynamic strengths using static cohesive constitutive laws. This is due to the, let's say, the intrinsic time scale that cohesive law has. So well, this is also some early work that we have done. So now we have like not only plain concrete, but we have a steel rebar. So we basically at the interface using a cohesive like element to model the interface, and the bulk element we still have cohesive elements. So this is another example, but for like more mixed mode fracture. And this is, let me see if this is our zoom how the fracture that has been propagated. What you can see at some point we have like a faster fracture, because this simulation I'm showing here, because it combines like both static and dynamic fracture. Well, this is some of our work. It's also on dynamic fracture, that is on, let me show it works the movie. A Dropowicz test, so which H00 is the plain concrete, H15 15 kilograms of steel fiber reinforcement, H45 is 45 kilograms steel concrete. What you can see is that how with adding more steel fibers, we have like prevented the central crack or the fracture crack, and also moved the, let's say, the mixed mode fracture or mixed mode crack to the right. So now let's come to the fracture in fiber reinforced concrete. So this is the part that I'm going to talk about. Start with that concrete. We know that is quasi-brittle. The structural fibers are often added to improve ductility and toughness indices at microscopic level. On the left, you can see from the stress versus the MOD curve. And you can see that as we add more steel fibers, the material behaves like more tend to from brittle to ductile behavior. And what we would like to do is that how can we numerically model such behavior. In the center, the two figures are the steel fibers observed in the CT scan. So with steel fibers, the steel fibers can be smooth or hooked ended, and the reinforcing effect is closely related with the fiber geometry. Such effect is characterized through a single fiber pull-out curve. What we can see, the figures, the top one, we have the smooth fiber, and the bottom one, we have like 3D, 4D, 5D steel fibers, depending on how many segments the fiber has. And the other effect is the fiber orientation. So we see here is that the single fiber pull-out test, what you can say is that the steel fiber can be oriented at different angles. In this case, in the experiment, it was carried out by Elisa Manuel, and it's at 0, 30, or 60 degrees. So these are the experimental results for 3D fibers and 4D fibers. You can see is that on the top row we have 0 degrees, 30 degrees, 60 degrees for 3D fibers, and on the bottom we have the same inclination angle for 4D fibers. What you can see is that for 3D fibers, as the inclination angle increases, we have like a more higher pull-out load for the, let's say, the second part, I would say. While for the 4D fibers, and at 0 degree, you can see that we still have like a brittle behavior. While at 60 degrees, most of the fiber has not broken before being pulled out. So in order to model this figure, we would like to see how can we go from the mesoscopic level to the microscopic level. In the mesoscopic level, it's like we need to model specifically the single fiber pull-out behavior. That's depending, of course, a lot on the interface. While on the microscopic level, if we have a 3-point bending test, we can see how the loading force versus the deflection. And for the mechanisms of fiber pull-out, what we specifically, because the pulling out test that Elisa Pauvet has carried out in the University of Nîmes, with several pulling speed, several loading velocities. So in 2020, we published work that basically we model the interface, but considering like dynamic friction, which is this mu here, this relation that's with mu 0, which is the static friction, and the V is the pulling the loading velocity. V0 is the reference velocity. This relation is adaptation of a dynamic friction from a work by James Rice. So by this we can model the rate-dependent friction, and the interface here, what you can say, this is in the 2D case, we explicitly model the fiber matrix interface, and the bump slip, of course, you have both the slip at the positive and negative direction, and then the compressive part is like a penalty, will work as just a normal compressive element. So boundary conditions and geometry, what you see here is that the three configurations we model the 0 degree, 30 degree, and 60 degrees, because this was the original work was done in Zhejiang University with one of the students I worked. And for the case of a 3D fibers, so this we can see that we can see the stress evolution in the fiber. So this is like on the left you have the pull-out load versus the extracted length. On the right, for the corresponding stages, we can see at what point the fiber, the steel fiber, has been pulled out. And I come back. Sorry, it's a little bit mixed up with the slides. This was the static pull-out that was done in the work with Zhang Hui in 2016 in Zhejiang University that I mentioned before. This is the case. It's the same methodology, the same concept, but the fibers are smooth fibers, and the test was static, because the experiment test was carried out by Chris Liang and Shapiro in 1999. What you see there is how the stress distribution during the process of being put out. So we come back to the work with the modeling of a 3D fiber. What you see here is that because we carried out the simulations in 2D, and there are some let's say some subtleties we need to have into account, is that we have to make sure that their interface, the contact interface, they have the same contact area, the same area, the same inertia of the area, and also the same area. So that's why you have this I shape of cross section that we modeled to have to satisfy the three equations you see there. Okay, and the simulations was for the fiber that we in the, let's say, longitudinal direction. You have 100, 150, and 200 divisions, just to see the influence of the mesh. So in the end, the calculations, we made it with 100 divisions. So this is a comparison with the experimental work, or the profile, the deformed profile, the hooked end fiber. Let's see, we capture quite well the area reduction was 21%. Also the local 3-point contact of strengthened fibers. So this is in the globally what is the experimental numerical comparison for pull out load versus the slip length for three velocities. 0.01 millimeter per second, it's like the static one, 0.1 millimeter per second, 1 millimeter per second, and for the three inclination angles. And this is the case for hooked end fibers. In globally, we have quite good comparison. So now let's come to the transition to, or the second level of the model. Let's say we are able to, at the mesoscopic level, capture well the pull-out behavior. How do we translate this behavior to the macroscopic or macroscopic level? So on the mesh, what you see, the first toy models that we have done is that we have all the fibers that being parallelly distributed, but each fiber carries a individual constitutive load depending which is its real inclination angle. And what you see here is that this is the first comparison we have for the three-point bending test, that if we model everything as 0 degree inclination, which means the fibers are the best taking advantage of, and the comparison with the percentage, different percentage of 0 degrees, 30 degrees, and 60 degrees. This is the case for volume ratio of 0.6 percentage. This is like 45 kilograms per cubic meter of steel fibers. Okay? So we can see what is the influence of the distribution of the fibers. Basically, you can say the first part, there's almost no influence at all, which means the fiber did not start working yet. So the effect of fibers are mostly after the first peak. And this is some simulations we have done depending on the influence of the fiber content. What you can say is that as we increase the fiber content, you have our post-peak behavior start to be from brittle to ductile and then almost hardening. And then we modeled the tests that this case, I think this is our dynamic. So what you see here is that the numerical one is the gray curve. This is for 3D fibers, which is a 10 millimeter length. And on the right, what you have is the load versus displacement curve. We have grouped all the experimental curves for 3D, 4D, and 5D. What you can say is as the 5D, you have like more segments of the fibers, and the reinforcement effect is stronger. We see that this is the result for 3D. Now let's say for 4D. And so we kept quite well, let's say until almost 2 millimeters of CMOD curve. And from then on, have some descriptions, but it's globally very well. And this is the case for 5D. And we still need to tune the parameter better in order to get a better global behavior. But in any case, it's we are very happy with the performance of this model. Okay, so now I come to the conclusions, that we have the explicit representation at the mesoscopic level, which allows us to capture all the physical phenomena such as friction rate effect that involved in the pull-out test. So the idea is that once we have the pull-out model works, we can generate a pull or date base of the fibers with all the possible directions and all the possible inclination angles, and then we assign this behavior to a constitutive level model to each fiber. So, and then using the concept of equivalent fibers, the macroscopic behavior of three-point bend beam can be modeled through the mesoscopic presentation. So this two-level or two-scale framework offers the possibility of incorporating the pull-out curves through analytical or experimental obtained pull-out curves. Okay, so this the curve below is this is some simulations that we've done with mesh-free methods with Pedro Navas with Madrid now. So in this case, we did not separate the fibers from the bulk material. So what we have is basically only changing the constitutive law of the uniform material, and then we have very good results. So next time we would like to, let's say, get more detail level at the mesoscopic simulations. Okay. So with this, I would like to finish the presentation. Fortunately, we